Polynomials is a branch of mathematics. In the topic of polynomials, we are going to discuss various types of expressions like variables, constants which come into existence. But before that, let's see the introduction of polynomials. What are polynomials? How do we define them in mathematics? Is what is today's session. When we come to the introduction of polynomials, let me come with the basic properties or the formulae which we have learnt in the lower classes. To recap with the formulae as learnt in the lower classes, one of the most famous formula is a plus b whole square or x plus y whole square. So let's see how we can expand this. We all know that this expansion is a plus b whole square is a square, that is x square plus 2ab, which is this, and b square, which is y square. So x plus y whole square is derived to be x square plus 2xy plus y square. We all know this formula because we have applied in many concepts in the lower classes. Now next comes how this is related to the polynomial. So let's see how this is related to the topic of polynomials as introduction. As we see here, every expansion expressed in the form of variables is a polynomial provided its powers are all whole numbers. Now what is the power of x? For the first term, x square, the power is 2. Next, the power of x is 1 and the power of y is also 1, and next comes the power of y in the third term, which is 2. For this to be a polynomial, the condition is that each of the powers must be whole numbers, as whole numbers of the real number system. So if all the powers belong to the whole number, then that whole expression is called a polynomial. A polynomial with the powers being whole numbers is how we define for a basic definition of polynomial. Let's take one more example. For example, I have x plus y whole cube, and I can expand this. We all know that a plus b whole cube is a cube plus 3a square b plus 3ab square plus y cube. And let's see if this is a polynomial. Now the variables here are identified to be x and y. The variables of the polynomial are the unknown constants which accept any real number. So x and y are just representation of the real numbers in the real number system. So any polynomial can accept all real numbers is how we define for the variables x and y, or only x for the polynomial. So for example, if I have this, I have the power of this to be 3, the power of this 2, the power of this 1, the power of this 1, this 2, and this 3. And I notice that each of the variable has the powers which are whole numbers, and therefore this belonging to w makes the whole of the polynomial, of the whole of the expression given out here, to be a polynomial. Polynomial is defined through the powers of the variables. If the powers of the variables are whole numbers, then the expression is a polynomial. If the powers of the variables are not whole numbers, then the whole expression cannot be defined as a polynomial. Let's see an example which is not a polynomial to understand the concept more better. For example, I have, say, p of x. I denote the polynomial with, say, for example, p of x, which indicates polynomial in variable x belonging to R. Then if I have this to be 3 plus 5 by x plus 4x minus 5x squared, and let's see how each of the powers are out here. Now 3, which is a constant, can be written as 3 times of 1, which indirectly can be written as 3 times of x power 0. So I have my constant with indirectly the power of the variable being 0, because x power 0 or a power 0 is 1, and therefore 3 written as 3 times 1, 3 times 1, which is x power 0. Therefore indirectly I extract from a constant the power of the variable is assumed to be 0 for any constant in the polynomial or in the expression. Next, if I have phi over x, this can be written as phi times of 1 by x, which is x raised to negative 1. So phi over x is phi times x raised to negative 1. Therefore, I assume the power of x in the second term is negative 1. Similarly, I have my third term out here, which is 4x. Therefore, the variable x has the power 1, and therefore I have 1 as the constant derived from the variable of the third term. Similarly, let's go to the fourth term. The fourth term has the power of x clearly seen out here to be 2, and therefore I just drop down 2 out here. Now let's check for each of the constants. I have the constant 0, minus 1, 1 and 2. Yes, this is a whole number, this is a whole number, this is a whole number, but this is not a whole number, because minus 1 does not belong to W, as discussed in the previous sessions. Therefore, since minus 1 does not belong to W, therefore the expression P of x given to be 3 plus phi over x plus 4x minus 5x squared denoted by px is not a polynomial. It fails to be a polynomial because one of its integral power, one of its power of x does not belong to W, the whole numbers. Therefore, P of x is not a polynomial. Is how I identify the definition of a polynomial from the powers of the variables, in this case x being the variable. Next, let's see the different types of polynomials. Now that we have defined what a polynomial is, let's classify the different types of polynomials existing in the branch of mathematics. Now, types of polynomials is the session. As we discussed about the definition of a polynomial, let's take, for example, a polynomial of one term. A polynomial can have any number of terms depending on the given problem. So what if it has one term? What if the polynomial has two terms or three terms or four terms or etc. and etc. So let's start with a polynomial which has one term. So let me take, for example, a polynomial P of x equals 4x. Surely this is a polynomial because its power is, the power of the variable is 1, which belongs to whole numbers. Therefore, P of x is a polynomial. Specifically, P of x is a polynomial of one term. There's only one term out here is what we need to notice. Now, in this case, any polynomial which has one term has got its specific name, which is called a monomial. A monomial is a polynomial which consists of only one term. Let's take one more example. How many terms out here? There are two terms. But is this a polynomial? Yes, of course. The power of x is 1. Each of 1 belong to whole number. Therefore, this given expression in the given example problem is a polynomial, but this is not a polynomial of two terms because this can be further simplified. Like 14x minus 2x, which can be further simplified to get 2x. So we need to simplify this further to get the most simplified form, and the most simplified form of the given problem 14x minus 12x is 2x. So this is the actual polynomial which intends to be decided on. Now here, the power of x is 1. It belongs to whole number. It's a polynomial, and it is a polynomial of one term, and therefore this polynomial indirectly given by this is a monomial. So the learning outcome in this example problem is that when a polynomial is decided for a monomial or any other polynomial of more than one term, we try to decide on simplifying the given polynomial to the most simplified form and then decide on the number of terms in the polynomial. The number of terms decide the definition of that particular polynomial. In this example, this being simplified to get 2x, and hence it's a monomial. Monomial is a polynomial which consists of only one term. So here I have the learning outcome which says monomial. It is a polynomial containing only one term. Is how we define the monomial, a polynomial with only one term. What if the polynomial is having only constant? Let's take an exceptional example in this case to understand the concept of monomial more stronger. For example, I have my function or the polynomial to be -3. Is this a polynomial is the biggest question before we decide on this polynomial being a monomial. So let's see if the given problem is a polynomial and then justify on that being a monomial. Clearly the function f of x here is given to be -3, and as we have discussed, -3 can be written as -3 times 1 because any number times 1 is that number itself. Now the reason why I multiply with 1 is to see that I can substitute this 1 with x power 0, because we all know that a power 0 equals 1, provided a is not equal to 0 is the condition. For a non-zero term, a power 0 is 1 for a not equal to 0 and for a belonging to R. So using that property, I have 1 which can be written as x power 0. So this is the polynomial indirectly for f of x. So that this is a polynomial because the power of x, which is 0, belongs to w, and thus satisfies the condition of the definition of a polynomial. So -3 x power 0 is a polynomial. So indirectly -3 is a polynomial, and it is a polynomial of one term because I have only one term out here, and therefore this is a monomial based on the definition of monomial is a polynomial containing only one term, and therefore is equal to -3 is a monomial. Is how I understand monomial as the definition of a polynomial with one term. Monomial is a polynomial of one term. The next type of polynomial after the discussion of monomial is binomial. So let's see what a binomial is in the branch of polynomials. As we see the word bi as taken from binomial, it clearly indicates that bi refers to 2, and monomial, which has mono, refers to 1, and therefore binomial refers to a polynomial of two terms. It's very simple that a polynomial which has one term is a monomial, and a polynomial which has two terms in its expression is called a binomial. Bi refers to 2 and mono refers to 1 is how we understand the definition of a binomial in the most simple manner. For example, if I take the polynomial p of x equals 3x minus 5x cubed. Now this expression clearly is said to have two terms, and let's see if this is a polynomial. To start with, the variable has the first term of the variable x has its power which is 1, and the second term has its power which is 3. The power of x is 1 and the power of x is 3, and we know that 1 and 3 both belong to whole numbers, and therefore by the definition of a polynomial, this is a polynomial. Now exclusively, this is a polynomial of two terms, the first term being 3x and the second term being negative 5 times of x. So a polynomial which has two terms, which is bi, hence a binomial. Therefore, since p of x has two terms, 3x and minus 5x, therefore p of x is a binomial, is how we understand the definition of a binomial using the properties of the polynomial. The next type of polynomial which we are going to discuss in the session is trinomial. Monomial, a polynomial of one term; binomial, a polynomial of two terms; trinomial, a polynomial of three terms. It's as simple as it is written out here. Trinomial. Tri refers to 3, and hence trinomial is a polynomial of 3 terms. This is how we understand the definition of a polynomial. For example, if I have p of x let's see if this is a trinomial or a monomial or a binomial. So in order to do an example problem of this sort in identifying for the type of a polynomial, we first try to simplify. As the condition says, the polynomial has to be in the most simplified form before we justify for that polynomial being of the 3 types. So let's try to simplify this polynomial before we justify on the trinomial case. So we need to first expand this, as we know that in the lower classes what we have learnt, we expand first 5 with this, and then we expand x with this. So each of the term of the first bracket is multiplied with the terms of the second bracket. That is how we understand the multiplication of 2 factors or 2 expressions. Now, as we multiply first 5 with this and x with this, then on further multiplication of 5 to each of the terms, 5 times this and this and this, and each of this multiplied to this, we come across 5 times 3 first, which is 15, then 5 times of x for the second term being 5x, and then 5 times of x square, which is 5x square, then x times of 3, which is 3x, and x times of x, which is x square, and x times of x square, which is x cubed, is how we understand the multiplication of each of the terms when expanded through the brackets. Let's try to further simplify this. As we see that this can be more further simplified by taking the constant here and then by pairing all the terms x one side together, and then I get this to be 5x plus 3x, which is 8x, is how we understand, and then minus 5x squared plus x squared, which is minus 4x squared, and then I get this to be minus x cubed. That's it, and I cannot further simplify this. This is the end of the polynomial. Now clearly I see that this polynomial, let's see if this is a polynomial. The power of x here is 0, and the power of x here is 1, and the power of x, the variable x, is 2, and the power of the variable x here is 3. Therefore, each of 0, 1, 2, 3 belong to the whole numbers, and therefore this is a polynomial. This polynomial has 4 terms, but a polynomial of 3 terms is a trinomial. Therefore, this cannot be a trinomial. the given example problem is not a trinomial. For a trinomial, the most simplified form must be of 3 terms. So here we conclude saying that this is not a trinomial. Is how we understand the concept of trinomial and not a trinomial. Let's take one more example to see if that is a trinomial. For example, I have this to be f of x equals 5 plus x minus 4x squared. Yes, in this case, the power is 0, the power is 1, the power is 2, and therefore all 3 belong to W, and hence because it has 3 terms, the first term being 5 and the second term is x and the third term is minus 4 times x raised to power 2, therefore it has 3 terms, and since it has 3 terms, it's a trinomial, a polynomial of 3 terms. Therefore f of x is a trinomial. It's a trinomial is how we conclude. Binomial, trinomial, and monomial is what we discussed as the different types of polynomials. Now let's take an exceptional problem and identify if that is a trinomial or a binomial or a monomial. For example, I have f is from x to x squared minus 3x plus 5x power minus 2. So let's see what kind of a polynomial or whether it's a polynomial or not. Now clearly I see that there are 3 terms, but I can call this to be a trinomial, but no, this is not a trinomial, because for a trinomial initially it needs to be a polynomial. So for the first term I see my power is 2, and for second time my power of the variable is 1, and for this my power of the variable is minus 2. 2 and 1 belong to whole number, but minus 2 is not a whole number. Since minus 2 does not belong to W, therefore it fails to be satisfying the definition or the rules to be defined for a polynomial. And therefore, with this rule breaking up, I say that the given function, therefore f from x to x squared minus 3x plus 5x is not a polynomial and hence is not a trinomial. Therefore, the condition for the given expression to be a type of a polynomial is that it needs to be a polynomial itself initially. So this is not a polynomial and hence not a trinomial, is how we conclude the given example problem. Next, let's discuss about the types of polynomials which are in 1 variable and 2 variable. That is, we're going to discuss about 1 variable polynomial and 2 variable polynomial or a 3 variable polynomial. In order to discuss that, let's classify the types of polynomials into 3 types. The first one is 1 variable polynomial. The second is 2 variable polynomial, and the third is 3 variable polynomial. So let's see each of the classifications of the types of polynomials: 1 variable, 2 variable, and 3 variable. So in this, as we have discussed, if the polynomial has only 1 variable, say for example, I have p of x is equal to 5 minus 3x plus 4x squared, then in this case the variable is only 1 variable. Therefore, such a polynomial which has only 1 variable x is called a 1 variable polynomial. What is a 2 variable polynomial? It concludes in the same manner as we have defined for 1 variable polynomial. That is, if I have 2 variable polynomial generally denoted by p of x comma y, then we clearly identify that there are two variables x and y in case of the polynomial px comma y. For example, if I take a polynomial of the form pxy is equal to x square plus xy plus y square, then this is a trinomial of two variables or a polynomial of two variables x and y. Here the variables being x comma y on the right hand side as expression. So this comes to be a two variable polynomial. Next, let's see a three variable polynomial followed by the two definitions coming from one variable to two variable and then three variable. It is quite obvious that a three variable polynomial would be defined as px, y and z. The three variables identified here are x, y and z. And for example, if I take a polynomial to be 3 minus 5x plus 4yz plus 2x square z cube, then I say this is an example of a three variable polynomial because it has three variables x, y and z. And interestingly, all these three are polynomials because they satisfy with the condition that the power of x here is 0 and the power of x here is 1 and the power of x is 2, which belong to whole number. And coming to the second example, the power of x is 2, the power of x is 1 and y also is 1 and the power of y is 2. So each of the powers of x and y taken independently are nothing but whole numbers, and hence the whole expression here is a polynomial of two variables x and y. Let's see the third polynomial of three variables. The power of 3 is 0, the power of x is 1, the power of y is 1 and the power of z is 1 and power of x is 2 and z is 3. As we see independently 0, 1, 1, 1, 2, 3, all the numbers belong to whole numbers. They all belong to W, and therefore this whole expression is a polynomial of three variables x, y and z. Two variable, one variable and three variable polynomials, the types of polynomials in the branch of mathematics. Next, degree of a polynomial. Let's see what is the degree of a polynomial in the branch of polynomials. Degree. Let's see what exactly the degree is by taking an example problem. For example, I have a polynomial p of x denoted by 3 minus 5x plus 4x cube minus 7x power 9. Now this is a polynomial of 4 terms, and clearly I see each of the powers of x are whole numbers, therefore it must definitely be a polynomial. It is a polynomial of 4 terms, and let's see what the degree is for this polynomial. The polynomial degree is generally denoted by degree of p of x is how we define, and this is nothing but the highest power of x. So degree of p of x in the most simple language is defined to be the highest value of the power of the variable. So what is the highest value of the power of the variable? As we take in this example problem p of x, which is 3 minus 5x plus 4x cube minus 7x raised to 9, I see that the power of variable x here is 0, the power of variable x in the second term is 1, and the power of variable x in the third term is 3. and the power of variable x in the fourth term is 9. So each term has its own variable value. Now here the first term has the power of x 0, the second term with 1, the third term with 3, and the fourth term with 9. Now the definition comes: the degree of the polynomial, the whole of the entire polynomial, is defined to be highest value of the power of the variable. Now which is the highest value of the power of the variable? We select the powers, and finally I find this to be the highest. This is the highest, and hence this is the degree of the given polynomial. Is how we understand the degree of the polynomial p of x. Therefore, degree of the given polynomial p of x is 9. Is how we understand in the most simple language. Let's see one more example to understand the concept more stronger. For example, I have p of x is equal to 7. Is it a polynomial? Yes, it is a polynomial. It's a polynomial which is called a monomial because this polynomial has only one term, that is 7. So it is a monomial with its highest power being 0, because this can be written as 7 times 1, 7 times x power 0, which comes out to be 0. So the power of the variable x here is 0, which belongs to w, and hence it is a polynomial. But as you see the definition, the highest value of this entire expression is nothing but the power of the variable x here itself, because there's only one term, and hence degree of p of x is 0. The given polynomial is 0. So what do we understand with this standard example out here? For any constant polynomial, that is a polynomial which is expressed as a constant, its degree is always 0, is the most important learning outcome with this example problem. Therefore, every polynomial which is a constant, or I call this as every constant polynomial, has degree 0, is the learning outcome which I make in this example problem. If a polynomial is a constant polynomial, just like p of x equal to 7, then its degree must be 0. It cannot have other than the value 0. Now let's see the coefficients of a polynomial. Now that we have discussed about the degree of a polynomial and the types of polynomials, now comes the question which raises on what would be the constants called in a polynomial. The variable x has its own definition. Similarly, the constant attached to that variable also has its own definition. For example, let's start with coefficients of polynomial. For example, I take the polynomial function p of x is equal to 4x cubed minus 3x squared minus 7x plus 9. Now in this case, it is a polynomial with 4 terms and it has the degree 3 because the highest degree here, or the highest value of the power x, is identified to be 3. So the degree of this polynomial is 3, and it is a polynomial consisting of 1, 2, 3 and 4 terms. Now let's see what are the coefficients. So coefficients for a polynomial are generally the constants which are multiplied or attached to the given variables or to the variables raised to any power. Here I identify the coefficients to be, for x cubed I have a constant 4 which is attached, and for x squared I have the constant attached which is negative 3. Even the sign takes into account. It's important that we take even the negative sign into account. For coefficient of x, the constant attached to x is -7 and the constant independent separately is 9. Therefore, here in this example problem, I identify that the coefficients of the polynomial p of x are 4, -3, -7 and 9 is how we identify the coefficients of the given polynomial. The coefficients are 4, -3, -7 and 9 for this given polynomial. Coefficients are the real numbers, constants, or the real constants attached to the variables is how we identify the coefficients for a polynomial. Now let's see some special type of polynomials in the topic of polynomials. The types of polynomials have their own types which we have discussed, but now let's enter into discussing the special types of polynomials. Zero polynomial plays a very vital role in the branch of mathematics. Though its significance is learnt in higher classes, let's discuss its definition as a special case. Special type of polynomial. Let's see what zero polynomial is defined in the topic of polynomials. A polynomial which equals to 0, a constant polynomial whose constant is 0. We know that a constant polynomial is a polynomial which just has its k belonging to R is called a constant polynomial, k being any real number. If that real number is exclusively the value 0, then this polynomial is called a zero polynomial. Is how we define the zero polynomial with its own definition. P of x equals 0 is called a zero polynomial. Now the coefficient of a zero polynomial is not defined because anything multiplied with 0 is 0. So we have the coefficient itself being 0, so we take it as an exceptional case, and hence it is a special type of the polynomial, which we're going to learn in higher classes. So zero polynomial is the constant 0 itself. What is its degree? The degree of a constant polynomial is 0, and hence the degree of the zero polynomial is also 0. Is 0. And moreover, because it has only one term, a zero polynomial is sometimes called a zero monomial. It is also called sometimes a zero monomial because p of x equal to 0 has only one term which is 0. Therefore, I can call the zero polynomial as a zero monomial with degree 0. Is how we understand the concept of the polynomial as a special case, with zero polynomial being a special case of the polynomials. Now let's see the polynomials which are classified through its degree value. Now that we have discussed about degree of a polynomial, let's now enter into taking the same degree definition into classifying the polynomials based on its degree value. Classification of polynomials based on its degree value is what we're going to discuss in the session. For example, I take a polynomial p of x, which is 4x minus 5, then I clearly see that with this example problem, p of x equals 4x minus 5, I have this to be, I have my p of x, which is 4x minus 5 with degree equal to 1, because the highest power of x here is 1, and for this it is 0, and the highest power being 1, degree is 1. Therefore, p of x, whose degree is 1, is given by the special name called linear polynomial. Any polynomial whose degree is 1 is defined to be a linear polynomial, irrespective of the number of terms existing. Next, let me take one more example. P of x is equal to 5x squared minus 4x plus 9. Now this polynomial has 3 terms. Let's see what exactly is the degree for this polynomial. When I take with the first term, the highest power is 2, and when I take with the second term, the power is 1, and when I take the third term, the power is 0. And therefore, when I decide on the highest value, 2 is the highest value, and therefore degree of p of x for this example problem is 2. So for this example problem, the degree is 2. And any polynomial whose degree is 1 is called a linear polynomial. Similarly, any polynomial whose degree is 2 is called a quadratic polynomial. It's how we define with degree 1 linear polynomial, with degree 2 quadratic polynomial, and degree 3 is what polynomial is what next we are going to investigate. So what is the name of the polynomial whose degree is 3? So let's take an example. Let's identify the degree. The power of x here is 0, the power of x is 1, the power of x is 3, and the power of x is 2, and deciding on the highest value, 3 is the highest value, and therefore for this example problem, degree is 3. And because the degree is 3, this polynomial is given by the name cubic polynomial. Cube stands for 3, quadratic stands for 2, linear stands for 1. So degree 3 stands for cubic polynomial. Is how we define the different types of degrees, defining the different types of polynomials. Degree 4 and degree 5 to be discussed has, if the degree is 5, if the degree is 4, then the polynomial is called quartic polynomial. And if the degree is 5, the polynomial is called quintic polynomial. This is out of the syllabus, but just for presumed knowledge, this degree 4 makes us quartic polynomial. Degree 5 makes a polynomial to be called a quintic polynomial. Linear, quadratic, cubic, quartic, quintic, etc. is how we define the polynomials classified based on its degree value. Now that we have discussed about the different types of properties which lead to understanding the polynomial more better, let's enter into solving some problems where I need to find the value of the polynomial at a particular value of the variable. Now, as the variable is a real number which can accept any real number, now my question comes, if I give a fixed value of the real number for that given value of x, what would be its respective polynomial value? So let's see in today's session about the polynomial value identified for the value at x. Polynomial value at a specific value of x belonging to the real numbers. is what we are going to discuss here. So for example, I have a polynomial p of x equals x squared minus 4x plus 6. Of course, this is a quadratic polynomial because its degree is 2, and it is also called a trinomial because it has 3 terms. Is how we define with the recap of all the properties we have learned. Now for this example problem, p of x equals x squared minus 4x plus 6, let's see what is its polynomial value at the question. For p of x equal to this, find p of x at x equals minus 1. So my question out here is, find the value of this polynomial at a specific value of x equals minus 1. So let's see how we can simplify. The given polynomial or the trinomial p of x is x squared minus 4x plus 6, and I need to find p of x at x equal to minus 1. So to find p of x at x equal to minus 1 implies I need to just find p of minus 1. The notation for finding p of x at x equal to minus 1 is defined as p of minus 1 because simply this value of x gets replaced with x, and therefore p of x changes to p of minus 1. And p of minus 1 is p of x being x squared minus 4x plus 6 when x is moved out and minus 1 is moved in. Similarly, each of x is moved out on the right side and each of minus 1 is moved in the respective places. Therefore, at x I get minus 1 whole square. At x here I get minus 1 and plus 6. So each of the x is being replaced with each of minus 1 equally on the right. Because it is being replaced with minus 1 on the left side, I equally replace on the right hand side, is how I understand this property. When I simplify this further, I get this to be minus 1 whole square, which is 1, minus 4 times minus 1, which is plus 4, because minus into minus is plus, and then comes plus 6. This, on further simplification, gives 6 plus 4, which is 10, 10 plus 1, which is 11. Therefore, p of x at x equal to minus 1 is understood as p of minus 1, which is more understood to be simplified with the value 11, is how I understand the polynomial value at a specific x belonging to R. In this case, the specific x being minus 1 through this example problem. So polynomial value can be found for that specific value by simply substituting that specific value in place of the variable x in the polynomial, as seen in this example problem. The next important definition in the continued session of polynomials is zeros of a polynomial. It is very important to understand the definition of zeros of a polynomial. So let's see in today's session about zeros of a polynomial. So in general, the word zero is coming into existence in this topic of zeros of a polynomial. So it has got definitely to do something with 0. Let's see how the definition comes more brief. Let me take the polynomial p of x. Now, zero of a polynomial is defined as zero of a polynomial p of x. Say for example, for p of x, the zeros of a polynomial p of x are the values of x for which this equal to 0. This is the main condition which makes us extract the value of x, and that x is called 0 of a polynomial. Let's see it more brief. The zeros of the polynomial p of x are defined as the values of x for which p of x equal to 0. So in order to find the zeros of the polynomial, we simply simplify this equation p of x equals 0, and then those values of x which are obtained are called zeros of the polynomial. Let's understand this concept more stronger by taking an example problem. This is the definition. Let's take an example problem. For example, I have my polynomial p of x is x squared minus 5x plus 6. It's a quadratic polynomial or a trinomial, x squared minus 5x plus 6. Now I want to find the zeros of this polynomial. Therefore, I go with this definition which says that in order that I find the zeros of this polynomial x squared minus 5x plus 6, I just take this equation and solve. So let's see how it is possible. The given polynomial, for zeros of the polynomial p of x, the condition says p of x must be 0. So for zeros, the condition is p of x equal to 0. Indirectly, the p of x being replaced with the given expression in the problem, that is p of x is x squared minus 5x plus 6 equals 0. And this, on further simplification, we know that this can be factorized using the quadratic factorization, and then x squared minus 5x plus 6 can be factorized to be x minus 2 times x minus 3, which is equal to 0, which on further simplification gives us, when the product of two factors is 0, this is 0 or this is 0, and which on continued further gives me the value of x is 2 and x is 3. Therefore, for this expression, zeros of the polynomial or the values of x for which this is 0. So taking p of x equal to 0 with the given expression equated to 0, I get the two values of x, which are 2 and 3, which are the zeros of the given polynomial p of x. Therefore, zeros of the polynomial p of x equals x squared minus 5x plus 6 are 2 and 3 is how we define the zeros of the given polynomial. X squared minus 5x plus 6 are 2 and 3. 2 and 3, the zeros for the given polynomial, is how we understand the definition. Equate the p of x to 0, find x, and that x is the 0 of the given polynomial p of x. It's simple. Now let's take an exceptional problem where I need to find for a constant polynomial the zeros. The zeros of a zero polynomial is what we're going to discuss in today's session. Zeros of a zero polynomial is the exceptional case which we're going to discuss in the session. Let's revisit the zero polynomial which we have defined as a polynomial which has the constant 0. So for this zero polynomial, I need to find the zeros, which itself says that the zeros of a polynomial is the values of x for which p of x equal to 0. Now the polynomial being the zero polynomial being the p of x equal to 0 itself, I have all x belonging to R. For all x belonging to real numbers, the zero polynomial does not lose its definition. It must be p of x equal to 0. Therefore, for every x belonging to R, p of x is 0, or for any x replaced with any real number, I get the value to be 0. Therefore, zeros of the zero polynomial are all real numbers is how I understand the zeros of the zero polynomial are all real numbers. Every real number when substituted in x for p of x gives me 0, and therefore zeros of the zero polynomial are all real numbers. Infinitely many real numbers belonging to R. In this session, we are going to discuss about the different terminologies used for zeros of a polynomial. As we know that the zeros of the polynomial are the values of x for which the function or the polynomial is equal to 0, we also have different names through which we understand the zeros of the polynomial. So let's see the different notations and the terminologies used in understanding the zeros of a polynomial. Zeros of a polynomial are also understood as roots of a polynomial, and they're also understood as solutions of the polynomial. Of a polynomial. These are the different ways through which we understand the zeros. If I want to find the roots of the polynomial, it is nothing but indirectly referred to finding zeros of the polynomial. If I want to find the solution of a polynomial or solve the polynomial, it is nothing but indirectly finding the zeros of the polynomial. It's how I understand the different terminologies used. Different terminologies for zeros of a polynomial. Is how I understand the different terminologies for zeros of a polynomial. Zeros are the roots, are the solutions for a given polynomial p of x with variable x. Now, as a specific case, let's take the special case of a linear polynomial. In order to find the zeros of the linear polynomial, we have always identified that a linear polynomial has only one zero. Let's try to investigate the linear polynomial with an example problem. When coming to the linear polynomial, and with zeros, let's try to investigate on the zeros of a linear polynomial. For example, I take the linear polynomial p of x is 4x minus 8 or 4x plus 8, and I want to find the zero of this linear polynomial which has degree equal to 1. So in this case, what I do is, in order to find the zeros of this polynomial, for zeros of p of x, the condition is p of x equal to 0. We know that as the basic definition. So for zeros of this equals 0, must be equal to 0. And then p of x indirectly out here is 4x plus 8, which is equal to 0. And 4x plus 8 equal to 0 implies minus 4. So I get this to be minus 2. Therefore, the zero of this linear polynomial is minus 2. So this is the zero. Is how we identify the zero of the linear polynomial. But interestingly, I also note a very important property here, that for every linear polynomial, there is only one zero, is how we conclude. So let's make the overall outcome, which says that every linear polynomial has one and only one zero is how we come through the learning outcome, is how we make the learning outcome, which says every linear polynomial has one and only one zero. It cannot have two zeros. A quadratic polynomial may have two zeros, or at the most may have two zeros or less than two. A cubic polynomial has at the most three zeros or less than three. It cannot have four zeros. A quartic polynomial cannot have five zeros, but at the most can have four zeros. A quintic polynomial can at the most have five zeros, but not more than five. Is how we make the learning outcome through this investigation. Next, we are going to enter into the concept of understanding remainder theorem through the definition of polynomials and the various properties of polynomials. How does polynomials lead to understanding remainder theorem? But before we understand the remainder theorem, which plays a very vital role in the branch of polynomials, let's see how the divisibility concept is essential to understand the remainder theorem. We need to understand the divisibility concept in brief before we try to enter into the theorem called the remainder theorem, the most significant theorem in polynomials. Divisibility. Let's try to understand the divisibility properties by taking a very simple example. For example, I have a number 5 divided by 3. I would like to divide a number 5 with 3. So here I understand that the number which is being divided by is called dividend. The term which I give for a number which is being divided by the other number is the dividend, and the number which acts in the division is the divisor. So this plays a role in dividing, because 3 gets divided, it is called the divisor. Now when the number is divided, we have learnt in the lower classes, the method of division is through this, wherein 5 divided by 3 is written out here, and then 3 ones are 3, which on subtraction gives me 5 minus 3, which is 2. This cannot be further simplified because this number is less than this. So we halt it here and we call this as remainder. And this is given by a specific name called quotient, and 5 is called the dividend and 3 is called the divisor. So the remainder, the quotient, the divisor and the dividend play a vital role in getting connected to each other. So each of these have their own properties, but they have their own mathematical relation connected, which says that the dividend, which is 5, as seen in this example problem, clearly is divisor times of quotient, which is 1, plus the remainder, which is 2. In every division concept, it holds true that the dividend is equal to the divisor times the quotient, that is 3 times 1 plus the remainder, which is 2, because this finally leads to 3 plus 2, which is equal to 5, which equals the dividend, is how we understand. Therefore, the divisibility property says if a number A is divided by B, that implies the dividend, which is A, is divisor times the quotient plus the remainder, is how we understand the divisibility property. Dividend is divisor into quotient plus remainder. dividend is A and divisor is B, is how we get. And more importantly, the remainder always lies and it is less than divisor. Is very important property which gets connected through this. Dividend is divisor into quotient plus remainder, and the remainder can never exceed divisor, and it is always positive. So 0 less than or equal to remainder less than divisor is how we understand the divisibility properties connecting the divisor, the dividend, the quotient and the remainder.